Everyone. Today we'll be discussing the LeetCode problem of the day, adjacent increasing subarray detection 1. In this problem, you are given an array of integers and an integer k, and you have to determine whether there exist two adjacent subarrays of length k such that both subarrays are strictly increasing. So he means you are given a array, and in that you have to check if you have two subarrays which are adjacent to each other. So this is one subarray and the next subarray, which is adjacent to the first subarray, and both of its size should be k, and the values should be increasing. So suppose you can have the values like 2, 4, 7, 9. If the k value is 2, k is 4. So in the first subarray, you can have the values like this, and the next subarray can be 1, 4, 6, 8. So in this case, these both subarrays are adjacent to each other and of length k, and both are strictly increasing. So in this case, you have to return true if you are able to find any such possibility. Otherwise, you have to return false. And note that the subarrays should be strictly increasing, so it can't have equal values. So this is not a strictly increasing subarray. So after 7, it must be only 8 or greater. So let's look at the first example. So we have this array and k equal to 3. So we can see that this is the first subarray 7, 8, 9, and this is a second subarray which is adjacent to it, which is also strictly increasing. So we return true. And if we check the second input, second example, we have k equal to 5. Let's see the first subarray of size k, 1, 2, 3, 4, 5. So this is not strictly increasing. And the adjacent one is also not strictly increasing. So we try to check the next one, but we can't form it because we can form the first subarray of size k, but the second subarray will only be formed up to size 4. So we only have one pair of adjacent subarrays, and that is also not strictly increasing, so we return false. Now let's go over the approach. So suppose we have this array and k equal to 5, and we just have to find a single subarray which is strictly increasing. So for that, we can start it here at index 0 and iterate on the first 5 elements and check whether all the elements are strictly increasing. If it's increasing, just you'll return true. Otherwise, you'll start at this index and you'll proceed the same process. Iterate on the next 5 elements and see if all are strictly increasing. So let's just go through this approach to see if we can optimize it in between anywhere. So we have this array, which is 2, and then 3, and then 4, and 3, and then it's again increasing. 2, 3, 4, 3, and then increasing. So first, what we do is you start here and you'll maintain a size which is initially 1. That means so far we have a subarray of size 1 which is strictly increasing, because only a single element is also considered to be strictly increasing. So once we have this, we'll start iterating. So you'll move to the next index. When you move to the next index, you'll see if your current value is strictly greater than the previous value, then you'll increase your count. So 2 and 3 is also increasing. After that, you'll move to 4. So 4 is also greater than the previous element. So size will be 3. Now after this, you can see that you have 3, and this is less than the previous element. So in this case, our increasing subarray breaks. So that means when you start at index 0, you can't find a subarray of size 5 which is strictly increasing. So that means when you start at this point, you don't get an answer. So ideally what you have to do is you have to start at the next index. But we can see from this diagram that when we started at index 0, we are not able to find increasing subarray of size 5 because there is a decreasing slope here. So that means even if we start at this point, we will still encounter this decreasing slope. And even if we start at this point, we will still encounter this decreasing slope. So from this, what we can see that if we have a decreasing slope, we can start our next subarray at this point, because if we start at any point previous than this, we will always encounter this decreasing slope, and it won't be a valid increasing subarray. So what it means is, when you have 3, which is violating the property, so 3 is not greater than the previous element. So what you do is, you will reset your size to be 1. So size is 1. So that means you are freshly starting at this point. And again, you'll repeat the same process. You will reach 5. So 5 is greater than 3. Size becomes 2. Then at 6, size becomes 3. At 7, size becomes 4. And at 8, size becomes 5. So in the iteration, at any point, if I see that my size is equal to k, I'll just return true. So the same approach, we can extend it for this problem where we have 2 subarrays. So let me just draw the array 2, 5, 7, 8, 9, 3, 4, 3, 1. And we have k equal to 3. So here we can maintain 2 pointers. So I will start from here, and since both the subarrays should be adjacent, so when it starts here, this is our subarray of size k. So ideally j should start here. So I is here, j is here. This is the starting points of the subarrays, and initially we will have size equal to 1. So this size is common because the size will be increasing evenly for both of the subarrays. So currently my size is 1, and I'll start my iteration from these points, because size 1 is always an increasing subarray. So that means I'll initialize my I equal to 1 and j equal to k plus 1 and start iterating. When I do the iteration, first I'll check if my current element is greater than the previous element for I, and the same thing for j as well. So 5 is greater than 2 and 9 is greater than 8. So that means it is still in the increasing slope. So size will become 2. And we'll do I++ and j++. Now again, we can see that 7 is greater than 5, but 2 is not greater than 9. So here the increasing property breaks. So what we do is, we just reset the size to be 1. So that means now this is our new starting point. So previously, these were our starting points, but now since the increasing nature has broken, so this we have reset the size to be 1, and this indicates this is the new starting point. And now just iterate. So size equal to 1, and we'll just move I++ and j++. So now 8 is greater than 7 and 3 is greater than 2. So we can safely increase the size. And then move the I and j. Now again check the condition. So 9 is greater than 8 and 4 is greater than 3. So size will become 3. So we can see that since size is 3 and that is equal to k, we'll just break the loop and return true. So we can also see our answer here. When we start here, this is our subarray of increasing, and immediately we have the next subarray which is also strictly increasing. Now let's code the approach we just discussed. So let's take 2 pointers. I will be at 1 and j will be at k plus 1. And let's just run a loop. You can just take the variables inside the for loop only. So int I equal to 1, comma j equal to k plus 1. And condition will be j is less than some sort length. Okay, this is a list, so we have to write size and then I plus plus as well as j plus plus. So now we'll first check if the increasing property is matching. So if start get I is greater than I minus 1, as well as we have to check for j as well. Start get j is greater than start get j minus 1. And we also need to take a size variable. So if these both are great, both are increasing, we increase the size, and otherwise we just reset the size. And at any point in the loop, if we have size equal to k, we can simply return true. And otherwise, at the end of the loop, we can just return false. Also, I think we need to handle a base case where k equal to 1. So if we have an array of size 2, suppose we have 4 and 6, 4 and 3 maybe. So since we are initializing I equal to 1 and j equal to k plus 1, so I will be at 1 and j will be at 2. So j is already going out of bound. So it will directly, this loop won't run and it will return false. But for k equal to 1, we can always, the answer will be always true. So we can have a base case k equal to 1, return true. Let me submit. Okay, wrong answer. Equal to 1, we are starting j equal to k plus 1. Now start get I is greater. And so initially when we start, since we are starting at I equal to 1 and j equal to k plus 1, that means we have already considered the I equal to 0 and j equal to k. So we have to start the size variable with 1. Yeah, now it works. Finally, let's do the time and space complexity analysis. So for the time complexity, we have a loop which is running from j equal to k to the num's length. So overall, the time complexity will be order of n. And space complexity will be constant because we are not initializing any arrays, only a size variable and I and j. So time complexity is order of n, space complexity is order of 1. I also have the code in Python if anyone wants to view it. I'll add it in the description as well. And let's catch up in the next video.